It is just past dawn on the roof of a hillside observatory outside Barcelona, and a thermometer that has been running for more than a century registers 40.5 degrees Celsius, 105 Fahrenheit. Nothing on the instrument is broken. It is simply doing what it has done every day since the 1890s, recording the air as it actually is. At almost the same hour, on the other side of the continent, a small German town near the Polish border logs 41.7 degrees, and across the country, more than 250 weather stations post all-time highs within a single week, more than have ever fallen together before. In the Netherlands, forecasters issue the nation's first-ever red heat warning, covering 8 provinces at once. Across the Atlantic, 160 million people in 30 American states wake up under an extreme heat advisory, and the country's Department of Energy declares its first-ever emergency for the grid that powers the Mid-Atlantic region, a network serving 65 million homes and businesses. Far below the surface of the sea, instruments on ocean buoys and satellites are logging something just as extraordinary. Sea surface temperatures higher than anything monitoring began, with marine heat waves by mid-year stretching across more than 80% of the world's ocean surface. None of this is happening in sequence. It is happening at once, on different continents, inside completely different systems, within the same few weeks. This is not a story about one hot summer. It is an investigation into a single physical process, a growing surplus of heat trapped inside the atmosphere and the ocean, and the way that surplus is now reaching into places that have nothing to do with the weather on the surface. Power grids, hospital wards, wheat fields, airport runways, insurance contracts, and the sleep cycles of hundreds of millions of people. Heat is no longer arriving as an occasional disruption and then leaving. It is becoming a baseline condition, one that the infrastructure of the last century was never designed to absorb. And the detail that keeps drawing scientists back to their data is not the heat itself, it is the pace. Records that climate models once placed decades in the future keep arriving now, years or even decades ahead of schedule. To understand why, it helps to stop looking at the thermometer for a moment and look instead at the air moving above it. In late spring of 2026, an intense heat wave rolled across Western Europe nearly a month earlier than the seasonal calendar would suggest, pushing temperatures across France and Britain more than 10 degrees Celsius above normal. The cause was not random. A dome of high pressure had settled over the region and simply refused to move, acting like a lid. It blocked fresh air from arriving, prevented clouds from forming, and sealed the hot air in place for days on end. These blocking patterns are not new to meteorology, but they used to dissolve quickly, pushed along by a fast-moving atmosphere. Increasingly, they stall. The same configuration can now sit in place for weeks, and that persistence is what turns an ordinary warm spell into an exhausting multi-week ordeal. That May 2026 event turned out to be only the opening act. Barely a month later, in June, the pattern repeated, this time even more forcefully, with almost no recovery time between one heat wave and the next for soils, ecosystems, or infrastructure already worn down by the one before. The explanation for that persistence sits several miles above the ground, in the fast-moving river of air known as the jet stream, which steers weather systems across entire continents. Its speed and predictability depend on the temperature difference between the poles and the tropics. The Arctic, however, is warming several times faster than the planet as a whole, a pattern scientists call Arctic amplification, and as that temperature gap narrows, a growing body of research links the change to a slower, wavier jet stream, one that stalls more easily and drags the weather systems it carries along with it. The exact strength of that connection is still debated among atmospheric scientists, but the practical effect shows up again and again in the data. A storm that once crossed a region in 2 or 3 days can now stall for a week. A blocking high can now sit in place for a month. At the same time, a warmer atmosphere is physically capable of holding more moisture, a relationship known to physicists since the 19th century, and every additional degree adds roughly 7% more capacity for water vapor. That has two consequences: heavier downpours in some places, and the thicker, more suffocating kind of heat in others, since humidity determines how effectively the human body can cool itself through sweat. Heat indices across parts of Western Europe in recent seasons have reached levels meteorologists classify as extreme heat stress. The last 11 years, essentially without exception, now rank among the warmest ever measured, and the 3-year stretch from 2023 through 2025 marked the first time in the instrumental record that a 3-year average had climbed above 1.5 degrees Celsius over the pre-industrial baseline, a threshold long treated as largely symbolic. None of this means extreme heat itself is new. What is new is the frequency, the duration, and the way separate heat waves now arrive stacked on top of one another against a warmer overall climate. For most of modern history, the ocean has quietly done humanity a favor. It absorbs more than 90% of the excess heat trapped by greenhouse gases, and for decades that absorption has softened the warming felt at the surface. But that buffering has limits, and instruments are now picking up signs of strain. Between 2023 and 2026, ocean temperatures across the ice-free waters that stretch from the edge of the Southern Ocean to the edge of the Arctic have run between roughly 0.35 and 0.73 degrees Celsius above the long-term average, with monthly anomalies occasionally reaching the highest levels ever recorded for that time of year. Part of the story is El Niño, the natural climate pattern in which unusually warm water pools across the tropical Pacific. When that natural cycle arrives on top of an ocean that has already been warmed by decades of accumulated heat, the effects do not simply add together, they compound. A warmer ocean releases more energy and more moisture into the atmosphere, fueling storms, intensifying rainfall, and extending heat waves over land. By the middle of 2026, marine heat waves covered an estimated 82% of the world's ocean surface, not a single region's anomaly, but something close to a planetary condition. One senior climate scientist described the situation carefully, noting that current ocean conditions could mark the beginning of a new phase for the climate system, a state without a clear precedent in the historical record. A warmer ocean also keeps the air above coastlines warm well into the night, at exactly the moment the land is supposed to be cooling down. That is where the story turns toward something far more personal than a chart of sea temperatures. Heat physicians use a specific term for a night that never cools below 20 degrees Celsius, 68 Fahrenheit, a tropical night. Not long ago, these were rare outside the actual tropics. Now, during extended heat waves, they have become routine, especially in cities. Specialists working on climate and health early warning programs point out that when it comes to assessing danger, the overnight low often matters more than the afternoon peak. The body needs a window of cooler air to let the cardiovascular system recover from a day of heat stress. And if that window never opens, the strain compounds night after night rather than resetting. The number of extreme heat days experienced by infants and older adults has risen by roughly 250% over the past decade. And in parts of Eastern Europe, older residents now face more than 30 such days in a single year. Health researchers add a caveat worth remembering. While older adults, infants, pregnant women, outdoor workers, and people with chronic heart or kidney conditions face the highest risk, heat stress can affect essentially anyone once the temperature stays high enough for long enough. And it is not only the most vulnerable who lose out. Studies tracking sleep through wearable devices across multiple countries have found a consistent link between higher nighttime temperatures and shorter, lower-quality sleep, and disrupted sleep is in turn associated with elevated cardiovascular risk and measurable declines in cognitive performance, an effect that quietly accumulates across an entire summer rather than fading after one bad night. Cities amplify all of this. Asphalt, concrete, glass, and steel, the raw materials of the modern skyline, absorb solar radiation through the day and release it slowly back into the air through the evening and overnight, a phenomenon known as the urban heat island effect. It can leave a dense downtown several degrees warmer than the surrounding countryside at the same moment in time, a gap that climate satellites can now map in striking detail, with surface temperatures across paved districts in southern France and northern Spain running noticeably higher than the fields and forests around them during a recent heat wave. Different cities are experimenting with different fixes. In Medellin, Colombia, roughly 8,000 newly planted trees have knit together a network of green corridors, and officials estimate the local heat island effect has dropped by about 2 degrees Celsius in some neighborhoods as a result. In Ahmedabad, India, community groups have coated the roofs of 17,000 homes in the city's least protected districts with reflective white paint. In Atlanta, after a detailed heat mapping study, the city now requires reflective materials on new and replacement roofs. Some cities lean on older, simpler tricks. Tokyo, Barcelona, Montreal, and Paris all run programs that spray water across pavement during extreme heat, since the evaporating moisture pulls heat out of the air near the ground, though the approach is limited by water availability and tends to be used only in the most vulnerable neighborhoods. Urban climate researchers are consistent on one point: no single fix does the job alone. It takes a combination of greenery, reflective surfaces, thoughtful planning, and deliberate protection for the districts that have historically received the least investment. When the temperature climbs, the strain moves straight into the electrical grid, as air conditioners switch on in millions of homes and offices at once. Space cooling already accounts for roughly 7% of global electricity generation, and that share keeps climbing alongside both temperatures and rising incomes in hot regions. In early July 2026, the operator running the largest regional grid on the American East Coast forecast a record summer demand, more than 166 gigawatts in the evening hours, higher than the previous summer peak set 2 decades earlier. The Department of Energy declared its first emergency for that grid, authorizing the largest data centers to switch temporarily to backup generators, so hospitals and other essential facilities would keep running without interruption. Wholesale electricity prices on that market spiked from under $40 to more than $1,600 per megawatt hour within a matter of hours, a direct signal that demand was pressing against the hard physical limits of the network. Energy analysts warn that the safety margin across a number of grids is shrinking faster than reserve capacity can be rebuilt, as aging transmission lines, the accelerated retirement of coal plants, and a surge in demand from data centers and electric vehicles collide with record heat, raising the odds that even a minor technical fault could cascade into a much larger outage. A decade ago, almost nobody building an electrical grid planned for the explosive growth of data centers built to run artificial intelligence systems. The largest of these facilities draw between 100 and 300 megawatts each, enough to power hundreds of thousands of homes, and researchers studying local climate impacts have found the ground surface around them runs roughly 2 degrees Celsius warmer than the surrounding area on average, occasionally as much as 9 degrees warmer at specific sites. A prolonged heat wave also removes the grid's room to maneuver. If nights never cool down, operators cannot take generating units offline for routine maintenance because demand never really drops, even after dark. The result is a closed loop. Heat drives up demand for cooling. That demand pushes the grid toward its limits, and a strained grid raises the odds of local outages on exactly the days when uninterrupted power matters most. There is a more hopeful thread running through the same story. During a severe heat wave that gripped Europe in 2025, record solar output actually helped keep the grid stable rather than pushing it toward collapse. On the hottest days, solar panels supplied up to 50 gigawatts of power in Germany alone, covering anywhere from a third to nearly 40% of the country's electricity use during precisely the hours when air conditioning demand peaked. There is a certain symmetry to it. The more intensely the sun beats down, driving the heat, the more power those same panels generate at the same time, partially offsetting the very demand the heat creates. A farmer cannot do what a factory can and simply relocate production to a milder climate. A field is bound to its soil, its season, and its water source, which is exactly why agriculture sits among the industries most exposed to extreme heat. A joint assessment from the United Nations Food and Agriculture Organization and the World Meteorological Organization lays out the scale plainly. For every additional degree of warming, yields of staple crops like wheat and corn fall by roughly 4 to 10%, and extreme heat simultaneously damages crops, stresses livestock, and depletes fish stocks, putting the livelihoods of an estimated 1.2 billion people at risk worldwide. In Brazil, a strong El Niño in 2023 and 2024, followed by prolonged drought, pushed daily maximum temperatures past the critical threshold for soybeans on repeated days, causing plants to drop their flowers before pollination and leaving grain formation incomplete, a combination that cut the national soybean harvest by nearly 10% that season. In the United States, agricultural officials reported that in 2026, 32% of winter wheat acreage would go unharvested due to heat, drought, and storms, the second highest abandonment rate since the Dust Bowl nearly a century earlier. The same story keeps resurfacing on other continents with different crops and different names. After a record heatwave in India in 2022, several states reported wheat yields down 9 to 34%, milk output down as much as 15% from heat-stressed dairy herds, and sharp declines in cool-season vegetables. An unusually warm spring across Central Asia helped trigger locust outbreaks and weak cereal harvests that same period, a chain reaction running from soil moisture through crops to insects and ultimately to food security across entire regions. Behind all of it sits a slower, steadier number. Atmospheric carbon dioxide reached roughly 432 parts per million by May 2026, the highest level ever directly measured, and most major crops begin showing physiological stress once temperatures climb past about 30 degrees Celsius, a threshold that is no longer an outlier, but a routine feature of summer in many farming regions. Behind every percentage point of lost yield stands a person, usually working outdoors, usually invisible to anyone not looking for them. Agricultural workers are roughly 35 times more likely to die from heat exposure on the job than workers in any other sector combined. And in 2021 alone, extreme heat cost the global economy an estimated 470 billion labor hours. Labor regulators in a growing number of countries are rewriting the underlying standards, introducing mandatory temperature thresholds above which employers must provide extra breaks, water, and shade, with some sectors granting workers the right to pause without losing pay once conditions turn genuinely dangerous. Construction, delivery, and logistics face similar pressure, with safety officials pushing the heaviest physical work into the early morning and mandating cooling breaks through the hottest hours. Retail and hospitality feel it too. Restaurants and cafes in heat-prone regions are investing in outdoor cooling and shaded seating. Grocery chains are shifting perishable deliveries to earlier hours. And organizers of outdoor concerts, fairs, and sporting events now budget for water stations, shade structures, and medical staff that would have seemed unnecessary only a few years ago. Transportation infrastructure is adjusting to a temperature range it was never engineered for. Steel rails expand further in sustained heat, forcing operators to impose temporary speed restrictions on vulnerable stretches of track. Asphalt softens and deteriorates faster under heavy traffic. Hot, less dense air occasionally forces airlines to cap the maximum takeoff weight of aircraft at particularly hot airports, since lift depends directly on air density. Underground transit systems face a related problem. Air conditioning built for one climate now runs at the edge of its capacity, and tunnels and stations absorb heat more slowly than the open air, but also release it far more slowly. So by the tail end of a prolonged heat wave, the temperature underground can end up higher than at street level. Logistics companies are shifting shipments of food and medicine toward the early morning and overnight hours, when the risk of spoilage or overheating drops sharply. None of these individual adjustments looks like a catastrophe on its own, but together they add up to a real economic drag in extra travel time and extra maintenance spending on infrastructure designed for a different climate. Prolonged heat also feeds directly into wildfire risk. Dry vegetation ignites more easily and burns more intensely, and flames spread faster through hot air. In Brazil, drought combined with the extreme heat of the 2023 to 2024 El Niño helped drive early destructive fires through the wetlands of the Pantanal, one of the largest freshwater ecosystems on the planet. A similar pattern played out in January 2026, when intense fires broke out almost simultaneously in Australia, Chile, and Patagonia, regions separated by thousands of miles but united by the same abnormally hot, dry season. Wildfire smoke travels hundreds or even thousands of miles on prevailing winds, and according to one major international health assessment, it contributes to roughly 154,000 deaths worldwide each year. Atmospheric monitoring agencies have responded by expanding air quality sensor networks and smoke forecasting systems that can warn residents in cities far from the fire itself about deteriorating air days in advance, a capability that barely existed a decade ago and is now becoming standard practice at weather services around the world. Burned landscapes, in turn, hold less moisture in the soil afterward, leaving the same ground more vulnerable to the next heat wave. One more example of a feedback loop that keeps reinforcing itself under the current climate. Heat rarely travels alone. It tends to arrive alongside drought, and the relationship runs in both directions, each intensifying the other. When soil dries out, less moisture remains near the surface to evaporate and cool the air just above it, the same basic mechanism that lets sweat cool the human body. Dry soil loses that cooling effect entirely, so incoming solar energy goes almost entirely into heating the air rather than evaporating water, which means dry regions warm noticeably faster than moist ones, and the hotter air then pulls what little remaining moisture is left out of the ground even faster. Climatologists watched exactly this pattern unfold across Western and Central Europe. A May heat wave left the soil parched, and by the time a June heat wave arrived, the moisture deficit had only deepened, with almost no recovery window between the two events, and river flows across the region running noticeably below normal. A similar picture is emerging across the American Great Plains and Southwest, where early season heat accelerates the evaporation of soil moisture and adds pressure to irrigation systems that depend on mountain snowpack and reservoir levels. Snow surveys across the mountain ranges that feed major rivers in the Northern Hemisphere point to a steady decline in winter snowpack in recent seasons, which translates into less meltwater available for irrigation and power generation during the exact stretch of summer when demand for both peaks. Water scarcity, in turn, limits the output of hydroelectric dams and constrains the cooling systems that thermal power plants depend on, adding yet another feedback loop. Heat drives up demand for electricity to run air conditioning. At the same moment, it reduces the capacity of some power plants to generate that electricity in the first place. Add up the consequences: lost labor hours, damaged harvests, strained grids, and it becomes clear that extreme heat stopped being purely a matter of comfort long ago. According to a major international health and climate assessment produced with more than 70 research institutions and the World Health Organization, lost labor hours cost the global economy roughly $1,090 billion in 2024 alone. The average person on the planet faced 16 days of dangerous heat that year that would not have occurred without the warming climate, and for infants and older adults, that figure rose above 20 days, 4 times higher than 2 decades earlier. A significant share of those lost hours falls on countries with hot climates and large outdoor workforces, from South Asia to West Africa, where the summer months were traditionally the busiest season for farming and construction, and are now increasingly becoming a season of forced downtime instead. Property insurance is a fast-growing line item in this story. Wildfires around Los Angeles in January 2025 cost the insurance industry roughly $41 billion, nearly a third of all insured global disaster losses that year. Hurricanes, floods, wildfires, and record heat waves are together pushing losses up so quickly that some insurers are simply declining to renew policies in higher-risk areas, with premiums in the most disaster-exposed parts of the United States rising nearly twice as fast as general inflation between 2018 and 2022. California's largest home insurer stopped writing new policies in wildfire-prone areas years ago, and after a string of destructive hurricanes, several regional insurers in Louisiana and Florida went under entirely, a sign that a market once built on spreading risk across many regions now increasingly faces correlated losses hitting several parts of the country at once. A few states are attempting reforms of their own. In Florida, lawmakers limited the legal costs insurers face in lawsuits, which state officials say has slowed the pace of premium increases compared with previous years, though none of these measures address the underlying driver of rising losses, which remains the intensity of the events themselves. The ripple effects reach further than any single premium. Economists at the Federal Reserve have found that a $500 increase in annual insurance premiums raises the odds of mortgage delinquency by roughly 20%, a chain that runs from the housing market straight into the financial stability of entire communities. A parallel dynamic is playing out in Europe around electricity costs. An analysis spanning 85 countries found that demand during extreme heat periods rises by nearly 40% in parts of southern Europe compared with an average month, and wholesale prices climb right alongside demand, doubling or tripling on the hottest days. Heat, unlike a flood or a single storm, does not arrive and then leave. It settles in as a background, steadily compounding load on infrastructure, labor markets, farming, and financial systems, all at the same time. A decade ago, the standard image of a European summer holiday barely changed from year to year. A Mediterranean coastline, guaranteed sunshine, a beach towel on warm sand. That formula is starting to break down. Not because the sea has grown any less inviting, but because temperatures at popular resorts increasingly push past the point of comfort and, at times, safety. Travel analysts now track a distinct pattern often called the coolcation, and searches for cooler destinations rose 74% year over year in the first half of 2026. Scandinavian countries have become some of the clearest beneficiaries, with a regional tourism report published in February 2026 showing bookings to Norway, Finland, and Iceland up 35% and forecasting 12 million additional visitors for the summer season ahead. Meanwhile, traditional southern destinations are seeing the opposite trend. Emergency rooms in Rome have treated tourists for heat exhaustion. Greek authorities have issued heat health warnings and closed the Acropolis during the hottest hours of the day, and Switzerland's Tourism Federation reports a marked rise in summer bookings to Zermatt, St. Moritz, and the Bernese Oberland. Interest in Greenland has surged as well, with the island's tourism ministry reporting that summer 2026 tours are already fully booked. Visitor numbers projected to climb 30% for the season, and 3 new airport projects making a once remote destination far more reachable for travelers from the United States, Britain, and Germany. This is not a wholesale retreat from Southern Europe, so much as a redistribution of demand across the calendar, with more travelers choosing May, June, September, or October over the traditional peak of July and August. A structural shift for an industry built around comfort and predictability as much as sunshine. Medicine is adapting on its own timeline, gradually rewriting protocols that once seemed sufficient. The World Meteorological Organization and the World Health Organization jointly maintain and continue to update guidance on extreme heat and early warning systems, work that now underpins national heat action plans in dozens of countries, ranging from color-coded risk alerts to specific hospital response protocols. Particular attention goes to higher-risk groups, older adults, young children, pregnant women, outdoor workers, people experiencing homelessness, and those with chronic illness, though heat stress can, under sufficiently severe and prolonged conditions, affect essentially anyone. Through a global health and heat information network, the World Meteorological Organization and partner United Nations agencies now give national and local governments the technical tools to prepare for rising risk in advance rather than simply responding after the fact. Opening cooling centers ahead of a heat wave, coordinating social services, and easing pressure on emergency rooms before temperatures peak rather than after. Everyday advice is shifting too. Physicians increasingly stress the overnight low as much as the daytime high, and city governments have begun taking steps that would have seemed excessive only a few years ago, including a temporary ban on alcohol in public spaces during a major outdoor festival in Paris, introduced specifically to reduce the risk of dehydration. The same reading on a thermometer carries very different levels of danger for different people, and the difference has less to do with age alone than with how well the surrounding infrastructure protects a given person. Air conditioning is a minor convenience for some and an unreachable luxury for others, priced out by equipment costs, electricity bills, or the simple unreliability of the local grid. Agricultural workers, whose jobs by definition offer no option to wait out a heat wave indoors, sit at the sharpest end of that risk. The same joint report cited earlier from the Food and Agriculture Organization and the World Meteorological Organization notes that a large share of the people whose livelihoods are threatened by extreme heat live in regions with limited access to irrigation, heat-resistant crop varieties, and early warning systems. It would be a mistake, though, to treat this purely as a story about poorer regions. Recent seasons have seen record temperatures broken in countries with some of the world's most developed infrastructure, including Denmark, the Netherlands, Switzerland, and Germany. The heat itself does not discriminate by geography. What varies is how expensive and how sustainable it is for a given society to absorb the consequences, and who ultimately bears the heaviest share of adapting when resources are not enough to go around. Perhaps the most striking part of this whole story is not any single broken record, but how often climate scientists find themselves saying the same thing. Reality is arriving faster than the models projected. A few years ago, many forecasts placed simultaneous, synchronized temperature records on land and at sea sometime around the middle of the century. Today, similar configurations show up almost every year. The director of one of Europe's leading climate monitoring services has echoed a warning voiced elsewhere in the scientific community. The system may be settling into genuinely uncharted territory. Part of the explanation lies in factors that used to be studied separately, now reinforcing one another. El Niño, the natural Pacific warming cycle, is now arriving on top of a baseline that has already been raised by decades of human-caused warming. And some researchers suggest that combination may help explain a curious pattern in the data. New records are increasingly landing just barely above the old ones, sometimes by only a few hundredths of a degree, rather than beating them by the wider margins that were once typical. That narrowing gap is consistent with a system settling toward a new, warmer equilibrium, rather than simply spiking temporarily. Though scientists are careful to note it is one plausible reading of the data rather than a settled conclusion. Another factor is the sheer speed at which the poles are losing their thermal separation from the rest of the planet. The gap between polar and tropical temperatures keeps narrowing faster than expected, directly reshaping the behavior of the jet stream described earlier. And forecasting models calibrated on decades of past data do not always keep pace with how quickly that dynamic is shifting in real time. Researchers increasingly treat heat waves, droughts, wildfires, and marine heat waves not as isolated events, but as links in a single causal chain, one that would have been difficult to predict by studying any of those components in isolation. It is worth being precise here. None of this means climate models have failed, and it would be an overstatement to claim scientists cannot explain what is happening. What the data increasingly shows is that certain compound events and regional extremes are landing at or beyond the upper edge of earlier projections, exposing real limits in how quickly forecasting tools adjust to a fast-changing baseline. Looking back across the first half of 2026, the pattern comes into sharp focus. The year opened with January ranking as the 5th warmest ever measured, and that same month produced a telling contradiction. A wandering, weakened jet stream drove severe cold across parts of the northern hemisphere, even as destructive wildfires tore through Australia, Chile, and Patagonia, followed by catastrophic flooding across southern Africa. March brought the 4th warmest month on record globally, and the 2nd warmest ocean surface temperatures ever measured for that month, with Europe posting its 2nd warmest March on record amid dry conditions, while the United States and Mexico saw an unusually early heat wave. Then came the 2 months that anchor this whole film. May turned into one of the most intense early season heat surges Western Europe has ever recorded, with temperature records falling across France, Portugal, Ireland, and the United Kingdom, and heat index values reaching what meteorologists classify as extreme heat stress. June set records on multiple fronts at once. The hottest June ever recorded for Western Europe, the 2nd hottest June globally, an all-time high ocean surface temperature for the month, and dozens of national temperature records, including 252 all-time highs across Germany alone, more than had ever fallen together before. By early July, a heat wave gripping the east coast of the United States pushed the grid serving 65 million customers into its first ever declared emergency, and ocean researchers reported that the first half of the year had been marked by exceptional sustained marine heat, confirming the ocean surface anomaly described earlier as the largest ever recorded in the satellite era. One energy specialist at a major American university warned that overnight temperatures during the heat wave offered almost no relief, preventing operators from taking generating units offline for maintenance and forcing several East Coast cities to impose local power restrictions to avoid a larger blackout. No single one of these episodes would have made headlines on its own. Strung together in chronological order across a single calendar year, they sketch the outline of a system that is, month after month, quietly establishing a new baseline, one the existing infrastructure was never built to handle. All of which returns to the question sitting underneath this entire film. Why do overloaded power grids, record-breaking ocean heat, damaged harvests, and shifting travel patterns keep showing up at the same time rather than taking turns? The answer traces back to a single process: a surplus of thermal energy accumulating inside the planet's climate system. The atmosphere, the ocean, and the land are all locked in constant energy exchange, and when more heat arrives than the system can radiate back into space, that surplus does not stay in one place. It spreads across every part of the system at once, simply at different speeds and in different forms. The ocean absorbs the largest share of that excess heat, which is why marine heat waves now cover such an outsized portion of its surface. A warmer ocean releases more energy and moisture into the atmosphere, which is why both flooding downpours and extended dry spells over land are intensifying at the same time. The shrinking temperature gap between the pole and the equator slows the jet stream, which is why blocking patterns can now stall over a single region for weeks. Air that stalls in place bakes the ground beneath it, which is why parched land heats up even faster the next time a heat wave rolls through. Power grids, farms, insurers, the travel industry, and hospitals are not responding to 5 different problems. Each is simply reacting through its own tools to the same underlying physical signal, which is exactly why heat now keeps turning up across such different sections of the news at once. If current trends hold, and climate scientists see little reason to expect a reversal in the near term, the synchronized nature of these records is likely to continue. The 3-year streak above the 1.5-degree threshold mentioned earlier is not a fluke, and its persistence has researchers watching closely for signs the system is settling into a new, warmer equilibrium faster than earlier models anticipated. Alongside the growing list of problems, a parallel track of response keeps expanding too. Renewable power, solar in particular, continues to grow, partially offsetting rising cooling demand, even as grid operators face the harder task of modernizing transmission infrastructure to withstand new peak loads. In agriculture, plant breeders are accelerating work on heat-tolerant crop varieties, and precision farming techniques increasingly use satellite soil moisture data to forecast heat damage before it happens. Cities continue expanding tree cover, reflective materials, and networks of public cooling centers, work that matters most in the places where a growing share of the world's population will be living by mid-century. Hospitals and emergency services are folding climate data more directly into daily operations. Building codes are shifting as well, with regulators in a number of countries revisiting insulation, ventilation, and maximum indoor temperature standards for buildings without air conditioning, while some cities now require greenery in new development approvals, changes that would have looked excessive a decade ago and are increasingly treated as standard practice on par with seismic or fire safety codes. None of this, climate scientists are quick to note, replaces the deeper task of slowing the accumulation of heat itself. Adaptation helps societies cope with consequences already locked in, but it does not address the underlying driver, the continued rise in greenhouse gas concentrations pushing the climate toward a new equilibrium. That is why the people working on this problem tend to describe it as 2 parallel tracks rather than one, adapting to changes that are now essentially unavoidable, while simultaneously working to slow the pace of further heat building up in the system. Back on that hillside outside Barcelona, the thermometer is still running, still logging every new day, every new heat wave, every fresh departure from what used to be normal. It does not draw conclusions. It simply keeps recording, with the same quiet consistency it has maintained for more than 100 years. And that consistency is the right lens for everything covered in this film. Extreme heat is not some entirely new phenomenon invented by the present moment. Hot years have always existed. What is different now is the character of the heat, how often it arrives, how long it lingers, how many systems it touches at once, and above all, how quickly infrastructure built for the climate of the last century is being forced to adapt to the climate of this one. Power grids are learning to withstand record peak loads. Cities are rethinking the materials used on rooftops and roads. Farmers are adjusting planting calendars and crop rotations. Insurers are recalculating risk models from the ground up. The travel industry is redrawing its own calendar. Hospitals are rewriting emergency protocols. Behind every one of these separate adjustments sits the same root cause: a growing surplus of heat inside the planet's climate system. And the fact that all of these shifts are happening on nearly every continent at nearly the same time says more than any single temperature record could. This is not a scattered collection of coincidences. It is a system undergoing a coordinated adjustment. This is not a story about doom, and it is not a story about a catastrophe too large to prepare for. It is the story of a planet whose climate system is entering a phase without a clean historical precedent, and therefore without a fully reliable forecast for the decades ahead. But it is also the story of a civilization that slowly, unevenly, and often behind schedule, is learning to live inside that new reality. Planting trees where there used to be bare pavement, painting rooftops white in places that never used to think about how much sunlight a roof reflects, timing solar power to match the exact hours cooling demand peaks, rewriting hospital protocols and harvest schedules alike. The most important discovery of the past few years is not another broken temperature record, since a record, in the end, is just a number on an instrument. It is the recognition that this is not a set of unrelated stories scattered across different corners of a hot summer. It is one interconnected system in which the atmosphere, the ocean, energy, food, health, and the economy are bound together more tightly than most people assumed even a decade ago. And the moment that connection becomes visible is the moment a society gains the one tool it actually needs to meet this new reality without being caught off guard. A clear understanding of what is happening, why it keeps happening in so many places at once, and what can realistically be done in response. The thermometer on that rooftop outside Barcelona will keep logging new numbers, and there is a fair chance next year's reading will surpass today's. But alongside those numbers, something else keeps growing too. The body of knowledge, tools, and solutions that a warming world is steadily learning to build in response.